So we've seen some examples with L'Hopital's rule. Let's get some practice with some other types. So remember that there are other indeterminate forms. A couple of them are if we have infinity minus infinity. And so here, oftentimes what we're going to try to do is get a common denominator or something like that. Get to a place where we have a single rational expression and then go from there. With the power forms of 0, 0, infinity to the 0, and 1 to the infinity, we're going to look at the log limit. I'll also say, you could have 0 to infinity, etc., variations of these. But the idea is that we would set the function inside the limit equal to y, and then log both sides, and then use properties of logs. Okay, we can eventually then move the limit inside the logs, or inside inside the exponential or the log, because we have continuous functions. So then we take the exponential and we're done. Okay, so we'll see an example of each of these for sure. Okay, so this first one, we want to get a common denominator, because right now if we were to evaluate it, we do get 0 minus, or infinity minus infinity. Okay, so if we get a common denominator, we would have limit as x approaches 1 of x ln x minus x minus 1 all over ln x minus 1. Okay, and then as we look at, if we try and take the limit of this, the numerator does go to 0, as does the denominator. Okay, I'll let you verify that on your own. Okay, so then what do I have to do? I have to use L'Hopital's rule. Okay, which says, okay, the limit doesn't change, but I take the derivative of the numerator and derivative of the denominator. When I take the derivative of the numerator and simplify it, I just get natural log of x. Okay, I'll let you verify this. I'm skipping through this for time purposes. And the denominator, I would write this as 1 plus 1 over x plus natural log of x. Okay, and now again, when I evaluate this, I get 0 in the numerator, 0 in the denominator. Actually, I missed a sign. Let me fix this. So this should be a minus 1 over x. Okay, so then I get 0 over 0 again. So what do I have to do? L'Hopital. Okay, L'Hopital says I get the limit as x approaches 1 of 1 over x all over 1 over x squared plus 1 over x, and this, as you substitute it in, you get 1/2. Okay, fun little exercise. All right, next one. So this again, I would have infinity times effectively 1 minus infinity. So this is indeterminate form. Okay, what do I do here? I can't find a common denominator, right? There isn't a denominator, but I notice that there is this 1 over x. So I'm going to try and rearrange it so that I have a denominator for each of these terms. So I'd have e to the 1 over x, and this x can move into the denominator as 1 over x. Okay, and then same thing with this denominator, 1 over x. Okay, so I'm just going to simplify this. We get limit as x goes to infinity of e to the 1 over x minus 1 all over 1 over x. Okay, and so now I notice that I have 1 over x. I don't like that too much, so what I'm going to do is I'm going to perform a substitution. I'm going to say y is equal to 1 over x, and that just, it's nicer so I don't have so many fractions going on, but then I notice if x goes to infinity, that means that y goes to 0. Okay, and specifically 0 from the right side, because this expression is never negative. Okay, on our domain at least. Okay, so then I can transform this into limit as y goes to 0 now of e to the y minus 1 over y. This is still indeterminate. Numerator goes to 0, denominator goes to 0. Okay, so then I have to use L'Hopital's rule and say this is the limit as y, that should be 0 to the plus, it goes to 0 from the right side, of e to the y over 1, and I can crank this out and I get 1. Okay, so with each of these, they do end up being different indeterminate forms. The first one was 0 over 0. The other one was infinity minus infinity. Okay, strategy in the first one is find a common denominator, and the second one, look for a denominator. All right, this third one, and then there are a few other ones. I'm going to just make the solutions available for you to follow through. This next one is really interesting. If you think about it from the very get-go, okay, this would approach 0 to the power of infinity, which we might just think, okay, that's 0, right? But is it? I don't know. Let's see. Okay. So this, for our purposes, is going to be indeterminate, but I mean, if you multiply 0 a handful of times, or infinitely many times together, you're probably going to get 0. But let's show it rigorously. Okay, so what I'm going to do is that since I have an infinity in the exponent, this means that I need to look at the log limit, meaning I'm going to let y equal, x to the power of 1 over x squared. Okay, and then this is where I would look at the log limit, so natural log both sides. Okay, and if I do that and rearrange slightly, I'd get natural log of x over x squared. Or, sorry, over 1 over x squared. Nope, just over x squared. There we go. Okay, and now what I want to do is, instead of looking at the limit of y, I'm going to look at the limit of e to the natural log of y. Okay, so this would be x going 0 to the right, and e to the natural log of x over x squared, which would be the natural log of y. Okay, again, the e to the ln y, the e to the ln would reduce and it would just be y. So this is equivalent. Okay, from here, what do I do? Well, I remember that the limit has a property of continuous functions, meaning that if I do the limit of the original function and I have a composition of functions, I can actually just look at the limit of the inside function. Okay, so I can move the limit into the exponent and say this is the limit of natural log of x over x squared. Okay, and then I test to see if it's indeterminate or not. Well, the numerator, that would go to minus infinity. The denominator, if I looked at that, that would go to 0, right? So is this indeterminate? I don't know. Okay, if this happens, we can't actually use L'Hopital's rule. We can't say that this is an indeterminate form. So what do? Well, I recognize that the limit exists for the denominator. It is 0. Okay, the limit exists as an infinite value for the numerator. So what I'm going to do is write this over again. Okay, I'm going to say that this is equal to e to the limit as x goes to 0 from the right, 1 over x squared times natural log of x. Okay, and I want to do the limit of that. And I wrote it this way because I'm thinking I might be able to use the product property of limits. So again, in order to use the limit properties, or the product property of limits, the limits need to exist. It doesn't say anything about exist as a finite number, so this is actually equal to e to the limit as x goes to 0 from the right of 1 over x squared times the limit as x goes to 0 from the right of natural log of x. Okay, so and I'll also say that these limits, since we have a one-sided limit, these limits do exist. If it was just the limit at 0, we could not do this. Okay, mainly because natural log of x isn't defined on the other side of 0, but we have a one-sided limit, so we can do this. All right, so then what I can do is evaluate each of these limits, and I get positive infinity times a negative infinity. Okay, so what in the world does this mean? We're taking an infinitely large positive number multiplied by an infinitely large negative number. Well, last time I checked, a positive times a negative is still a negative. Okay, and so if we think about the exponential decay, or if we think about the function e and where it's at minus infinity, this is 0. Okay, so our suspicion at the beginning did hold true that 0 to an infinite number of times is 0, but we had to go through a long process to get there. Now, in here, did I use L'Hopital's rule? No. Okay, and that's okay. Remember, you might not always need to, and that's a skill worth recognizing too. But what I did do that you may need to use L'Hopital's rule for is looking at the log limit. Okay, so try, if you're given this original function, try changing perspective to a log limit too. They're equivalent in value. You just need to make sure to do the work. Okay, so interesting exercise. The last two examples, I want you to pause the video, try them yourself, and then when you're ready, resume the video to see the solution. And here are the answers. So in the first one, look at the log limit, and then once you do that, you get some nice simplification. What I ended up doing at the end, so in here I didn't do e to the ln right away. What I did is I found kind of the log limit first, and then I took e to that answer. Okay, remember, if you do it this way, you just have to exponentiate at the end. In the previous example, I ended up doing the exponentiation and logging all in one step. Okay, same sort of thing with this last one. I looked at the log of this first and looked at the log limit, and then once I've computed the limit, then I raised it to the exponential. I exponentiated it, I guess. I think that's a word. Hopefully it's a word. Okay, so just some more exercises for you to try, and we'll get some more practice in class.